Hello everyone, this is Reza Vazi, and on this video I'm going to cover the basics of clusterings, specifically k-means clustering. Clustering is an unsupervised data mining method. It means that there is no target variable. Also, it is known as exploratory or descriptive analysis. Basically, it is the process of finding meaningful groups in your data, or the process of grouping bunch of observations that are similar to each other in your dataset. The goal is not predicting here, it is exploring. You are trying to see how many groups you can come up with, how many distinct groups you can come up with in your data, or how many distinct groups are available in your data. Clustering has many applications. Its application in marketing comes from consumer or customer segmentation, where you want to identify different groups of customers that you can develop a specific marketing material for those groups. Another application of marketing clustering in marketing is clustering voters, where you want to know how voters belonging to each group would respond to different political stimulus, and you want to use that knowledge to improve your campaign, your political campaign efficiency and effectiveness by tailoring the material and tailoring the channel that you are going to contact those group of voters. Another application of clustering is in document clustering, in which tries to group similar text together. Basically, in text analysis, in text mining, you can use clustering to help you understand your text content a little bit better. And another application, one final application that I'm going to go through here in this recording is session grouping and click-stream analysis. One click-stream profile may be that of customers who know what they want and proceed straight to checkout. Another profile may be that of customers that research the product, read through reviews, and make a purchase during later sessions. So how you treat these customers, how you encourage them to buy your items are totally different. Please remember the applications of clusterings are not really limited to these three categories that are covered. There are a lot more applications. There are applications of clusterings in medicine, there are applications of clustering in sports science, and everywhere that you want to see if your data group together and if you can drive any meaning or any insight out of these groups, the clustering will help you to do that. As I said, clustering always tries to group similar data points together regardless of the type of clustering. And you can identify two general algorithms or two general types for clustering. One set of clustering methodologies or algorithm will ask for the number of clusters you want to identify in your dataset. So you should assign a number before you can run or you can apply the clustering algorithm, the clustering methodology. You tell the methodology that you want to see 2 groups, 3 groups, 4 groups, or as many groups that make sense in your context. There are other sets of clustering methodologies that will do this for you automatically. So they do not ask how many clusters or how many groups you want to be identified in your group. They will go ahead and try to divide your observations, your dataset, to a number of groups that are distinct from each other without asking you how many groups you want to see in advance. So they basically will give you as many groups as it is possible for the algorithm to clearly distinguish from each other. You can also categorize clustering algorithms based on the cluster types that they generate. You can have exclusive strict partitioning clusters, which they do not have any overlap. Each member of cluster only belongs to one cluster and that's it. You can have overlapping clusters, which one member can belong to more than one cluster, such as high profit customers and high volume. So you have a cluster for high profit, you will have a cluster for high volume customers, and you can have customers that belong to both clusters. You can also have hierarchical clusters where you will have parent and child type of relationship. An example is high profit customers with long term and new customers as childs. So at the higher level, more abstract level, you have high profit customers, that's the bigger group, and then you'll have two smaller group within that big high profit customers group, and those groups are long-term customers and new customers. And the last type is probabilistic or fuzzy clustering, in which the algorithm will give you a probability for each of your observation, each of your data sets, as what cluster they belong to. So let's say that you have a total of 3 clusters. There will be a 3 different probability for each observation, telling you the probability or the chance that that observation or that data record will belong to any of these clusters. Now let's focus on one clustering methodology or algorithm. It is called k-means clustering. K-means clustering is very simple and is one of the most commonly used clustering methodologies in the industry. K in the k-means refers to the number of clusters which is identified by the analyst, which is going to be you. So you will be in charge of deciding what is the appropriate number of clusters that you want this methodology to generate for you. K-means algorithm looks for a prototype data point, or as it called centroid, for each cluster. Centroid in k-means clustering is the mean of all data points in a specific cluster, and it does not have to be a real point, or it does not have to be a real data point. In some software you can force it to be a real data point that exists in your dataset, but it does not necessarily have to be a real data point. Centroid refers to the average or the mean of all data points that belong to one cluster. So the number of centroids is equal to the number of clusters, which is equal to k. Overview the k-means algorithm. Let's go through the k-means algorithm in general terms. The algorithm starts with initiating k random centroids. Basically, if k is equal to 2, it will go ahead and randomly select 2 points, assigns 2 points as the centroids. Then after this, starts assigning data points to centroids based on their distance from those centroids. So those points in your dataset that are closer to centroid 1 will be assigned to centroid 1, and those who are closer to centroid 2 will be assigned to centroid 2. Then after this process, the algorithm calculates new centroid values, which is the real mean or average of the points in each groups. After doing this, it will go through another round of assignment. This time again tries to assign points based on the new centroid. Your centroid has moved, and now maybe new points will be qualified to join this new to join this cluster, and some points will not be qualified to be included in this cluster anymore, and they will be moved to another cluster. And this process continues until no new centroid can be identified, until the new centroid, the new calculated centroid, is equal to the previous centroid, and no new data point assignment occurs. Now let's gain a better understanding on how k-means clustering work by going through this visualization. You can either click on this link if you have the PowerPoint slides, or you can go ahead and search Google for visualizing k-means. The result with naftaliharris.com website is the one that you want to click on. It should be either the first result or the second on the list of Google search results. Let's go ahead and do this so you can actually get a better understanding of how k-means work. Here's the website, the Naftali Harris website, and the first thing you need to decide is how to pick the initial centroid. You can go ahead and choose the centroid yourself, or you can use another method called forest point. Let's go and choose the initial centroid randomly, and then you will have a bunch of choices on how your data will look, your data look like. Let's go with Gaussian mixture. So here, as you can see, we have three distinct groups, and let's go ahead and see how this k-means clustering works. The first step is to add centroid. So we can see that we have three groups. Let's go ahead and add three centroids. 1, 2, and 3. So these are three randomly selected centroids. Two of them are very close together, another one is very far. Now let's go ahead to the next step. Next step is to assign data points to these centroids. Now think about it. Which data points will be assigned to the blue centroid? Which data points will be assigned to the red centroid? Let's go to the next step. On this step, it actually assigned the points to these groups. So you can see the data points have changed color, and we have the blue group data point, red, and green. We have three segments or three clusters. Let's go ahead and update the centroid. When we update the centroid, it will go ahead and calculate the new mean. Can you guess where the new mean for this blue group will fall? It should be somewhere here. It's the mean of these blue dots or these blue data points. It should be somewhere here. Let's go ahead and update centroid, and the mean for the green should be somewhere here, and the mean for the red should be somewhere here. Let's go ahead and update the centroid. Yes, it changed. Now we can go ahead and reassign the points. The points will be reassigned to the centroid closest to them. So all these blues will be reassigned to the red ones, and there will not be much reassignment for greens and blues on this side. Now you can go ahead and update the centroid. When you update the centroid, the blue centroid will move more towards the blue, the green centroid should not move at all, and the red centroid should move towards the center. That's it. And we can go ahead through another reassignment, but do you think if I click on the reassigned point, anything will change? Nothing can change. You can go ahead and update the centroid, but do you think that the centroid will change? No, it didn't change. Then you can go ahead, reassign, update. This is the point where the algorithm comes to an end, because there will be no change in assignment and no change in the centroids anymore. At the end, you may ask, so how do we know these clusters are good, these clusters are valid, and we can rely on them? There is no easy answer for this question. When it comes to unsupervised or descriptive methods, you have to rely a lot more on your domain knowledge, your data understanding, and analysis goal to evaluate the reliability and accuracy of the results. However, there are some measures, some mathematical and statistical measures that can give you a better understanding of how your clustering algorithm is doing. And the two are SSE, or sum of squared errors, and Davis-Baldwin index. In general, the lower the value of these measures, the better the clustering, but not always. Why not? Because it's a scale dependent task. Sometimes you are dealing with values in thousands, then the SSE of 1 or SSE less than 1 is really good. It's super good. Sometimes you are dealing with values in 1/10 or 100ths, then SSE close to 1 is not good, it's disastrous. So you have to look at this scale as well. Good models will have low SSE within cluster and low overall SSE among all clusters. The DV index is a measure of uniqueness of the clusters and takes into consideration both cohesiveness of the cluster, which is the distance between data points and the center of the cluster, and the separation between clusters. It is the function of the relation of within cluster separation to separation between the clusters. both DB and SSE have limitations of not guaranteeing a better clustering when they have lower scores. So in general, the lower the better, but not always, and you'll have to look at the scale of the measures of the variables involved in the clustering as well, especially when you are looking at the sum of the squared errors. Again, at the end, the best tool that you have in evaluating how good your k-means clustering tasks have been is your experience, your domain knowledge, and your understanding of the data. Good luck.